Hi, welcome to the Calculus 2 lecture series. And we are starting unit number 3 today. In unit number 3, we're going to talk some further applications of integrations. And we are going to focus on the two topics. We're going to talk about the arc length and the surface area of a revolution. In our first unit for the Calculus 2, we kind of focus on how to find the area between two curves and how to find the volumes, right? So now we are going to talk about how to find the surface area and the arc length. Okay, so now let's start our lecture number 13. So in the lecture number 13, we're going to talk about the arc lengths here. Okay, let's go ahead and go to our lecture notes. All right, so for this section, the key concept we're going to cover, it will be, okay, the first ones here, we're going to talk about the length of the curves here. And then the second topic in this ones here, we're going to talk about the arc length functions and its derivative. Okay, so before we start to work on some example, let's take a look at the arc length formulas here. Okay, so let's see here, what is the formula looks like? So if we say, if you have functions here, if the f prime x, all right, so if x prime x is continuous on the specific interval, we say is the AB, then the length of the curve y equal to the f of x, and with x is between a and b. That's how do we define that the length will be that you're integrating from the a to b, and then here it will be 1 plus f prime x, the square, all right, and the dx here. So what is we try to, this formula try to find here is like in here, okay, so like if I have a functions here, and then this is my A, this is my B's, right? So between the A and the B's here, I'm going to looking for the length of here. Okay, so how do I get the length of these functions here? That's how it's this one, that this formula is, will tell us about. How about if I have functions that similarly, okay, so if I have a function is with the x is a function of the y's here, so we can write it here is L is equal to C to D here. Then the same ways here, you can write it as 1 plus G prime Y, and the whole thing squares here, then is the dy. Okay, so this is the situation. If it's the x, if x is a function of the y's here, right? So like this is the situation. And then if you have functions here, x is a function of the y's here, like some function of here. And then you have the, like in the C and the D's here, C and the D, then you want to find this length, right? So what is the length of this curve? Then you'll be able to use this formula. It's a similar, it's very similar. You just change it to the dy dx, change the dx to dy's here. And in here, I'm not really trying to prove it. I just want to show you the basic, why the arc length formula is here. It's very, very similar. Like when we first started integration, we talk about the Riemann sums, right? Riemann sums here about the rectangle area. Then you try to approximate the area under the curves here. Okay, so now let's take a look here. Okay, so the idea for here is the same here. Okay, so now let's take a look if here is your functions here. I see here, this is, okay. So this is the functions here. Now let's say here, this is like maybe this is a P0, this is a P1, this is a P2, this is a P3, this is a P4, P5, P6, P7, right? Okay, so for example, this is my A, and this is my B's, right? Okay, so this is my A, this is my B's here. Okay, I'm going to find the length of this function from A to B. So by similar, like the Riemann sum concept here, right? So I can say, instead of the curve, I can connect these 2 points by a line. Can I? Yeah, so then I can connect these 2 points by a line, these 2 points by a line, and these 2 points by the line, these 2 points by the line, these 2 points by the line, these 2 points by the line. So that basically, then you will say, hey, the length of this curves here, right? I can try to just add all these lines together. And as you can see, if in here, I kind of divide it to the many subintervals, then this line will be very close to the curves here, right? So now I can say the limits here, the length here really is just like a Riemann sum concept. So it's limit n approach to infinity, and then the summation for the each segments here. So that's why I can use the pi minus 1 to the pi. This is the segment between I minus 1 and I. So I went from 1 to infinities, right? Okay, so now for each pi, so what is this pi minus 1 and the pi? Right, so remember by the distance formulas here. So for each one is here. So for example, this is a P1. I have x1, I have x2, I have x3, I have x4, so right, x5, it's like that. So each one's here by the, by the distance formula, the xi corresponding to yi, right? So the distance formula will just be x. So it would be xi minus xi minus 1 squares, right? Then plus yi minus y the I minus 1 square. Okay, so that means my, in here, I am doing what? I'm finding the differences here and then the differences here, right? So the differences for each xi and xi minus 1, I can call that this is delta x. Is correct? And then this is the y differences here, right? So this is yi and yi minus 1. So this one's here, I can call what? I can call the d delta y's, right? So for here, then I know this one's here, I can try to. So I will say this will be the delta x from the xi to xi minus 1, the differences plus what delta y squared, right? And the delta y square, and then we know, okay, so this is, okay, so by the, if you still remember, by the mean value theory, right? So by the mean value series, we know the f of xi minus f of xi minus 1 is equal to what? is equal to, you have to find some value I call the xi star. And then here, this is xi minus xi minus 1, right? So now in here, this is yi basically, right? So this one is what? This one is our delta yi, right? And this is what? This is my f prime xi star. What is here? This is delta x, correct? All right, so now I can replace this one here. Okay, let's take a look here. So then my length of this segments will be equal to what? Will be equal to delta x squared plus delta yi, right? So will be what? Will be f prime xi and what? Delta x what? Square, correct? You just use the mean value series to replace the delta yi equal to the f of xi and delta xi squared. Okay, so now for here, okay, let's go to here. So for this ones here, then you will have what? You will have delta x squared plus got another delta x squared, right? So you have f prime xi square delta x squares, right? So you can factor the delta x out. Oh, so here is delta x. So what is your inside of the square root is 1 minus f prime xi what? Xi squares, right? So since we know, a while ago we said limit n approach to infinity of the pi minus 1 pi. All right, so forgot to put the summations here, right? So the limit summation I from 1 to n, the pi minus 1, the pi will be equal to what? Will be equal to similar is the limit n approach to infinity, summation I from 1 to infinity. And then this will be 1 plus f prime xi star the square times delta x. This one is what? This is based on the Riemann-Sum concept, right? So delta x will become what? Will become the dx, and then this whole thing is based on the Riemann-Sum concept will be turned to what? The integration of a to b. Then what is here? This is 1 plus f prime x squared times what? The dx. So that's why the formula is very, very beautiful. And in here, the reason why I specifically kind of give you a quick proofs here is basically I just want to see this is really is applied the Riemann-Sum concept. When we first introduced the integrations, we want to find the area under the curve. That's exactly what we did, right? We divided into many, many sub-intervals. Then for each sub-interval, we find the area. Then we add the area. Then we let the limit n approach to infinity. Then that's how we define the integration. Okay, so now in here, after you know the formula, then really the problems here will become pretty easy. Then you just need to apply all the technique, integration technique you learned previously, correct? All right, so now let's hear. So in here, we want to find the length of the arc of the semi-cubical parabola y squared equal to the x cubed between the point 1, 1 and 4, 8. So like in the graph, if you graph this function, this is what is the function going to be giving you. So that's why they want to find this ones here. Okay, so it's the top, the half of the curve, right? So because we are looking for the top half of curve from the graph, see here. So I will have y is equal to what? You take the square roots, so it's x to the 3/2. It's a positive because I have the top half. Now I need to take a dy dx or f primes, right? So the dy dx is the 3/2 of x what? X to the 1/2 here, right? So this is my f prime x also. correct? Okay, so now let me try to find the length. The length will be A to B, so X is from 1 to where? From 1 to 4. Then the square root of 1 plus F prime X, so it's 3/2 X to the 1/2, the whole thing square, dx is here, right? So let's see here. So this is 1/4. And then what is here? So here is 1 plus 9/4 and to the x, correct? And the dx. So that's why we say this is a further applications, right? So after you know what we're looking for, we substitute to this formula we just derived, then the remaining will just be your integration skill, right? So now you see here 1 plus 9/4. So how do I solve it? You say, oh, I can use u sub. So I will say 1 plus 9/4x. Now I have a du is equal to the 9/4 dx. So now I know the 4/9 du is equal to the dx here. Okay, so now my length, I can substitute the limits, right? So this one I can substitute here. So then I have a 4/9. I move the 4/9 to the front. So 4/9 square root of the u du. And then you can substitute the x, the upper bound and the lower bound. So the lower bound, so when x equal to 1, so what is u? U will be 13/4, right? So when x equal to 4, what is u? U will be 10. So you can say this is a 13/4 to the 10. Just integrate the square root of the u. So this will be 4u, right? And then this is a 2/3, u to the 3/2. Then you plug in 10 and 13/4. Or you can just, after you integrate the u, then you substitute back the x, and then you can use the original, the original limit. So after substitute, this is what I have here. So the final answer is 1/27. Then this is 80, and the square root of the 10 minus the 13 square root of the 13 here. Okay. So like I said, the remaining part is just use your integration skill. Okay, now let's take a look. So what is the length of the arc given by x equal to the 1 plus 1/3? So this is the, the formula we just talked about here is these green ones, right? So if x is a function of the y, then instead of integrating to x, we need to integrate into y here, all right? So now let's do the same things here. So we'll say the dx dy. So take the derivative of y. So what is this one? So it's 3/2 and the y to the 1/2. Correct? Okay. So now we will have L is equal to y is from 0 to 4. Then here this is what is 1 plus 3/2 y to the 1/2 to the what square, right? dy. And then here will be 0 to the 4. And then this is 1 plus 9/4 to the y dy. Whoa, very, very similar like we have before. So we can say do a u sub 1, u is equal to 1 plus 9/4y. So the du is equal to 9/4 dy. And then is 4/9 du is equal to dy. See here, right? So now I replace it. So this will be 4/9 in the front, and this will be the u du. Okay, so when x equal to 0 and the u equal to what? U equal to 1. When x equal to 4, what is in here? Well, u is equal to 10. So this is from 1 to what? 1 to 10. Correct. All right. So now I'm integrating that. So this will be a over 27 u to the 3/2. Then you have a 10 to the 1. So this will be a over 27. And then I have a 10, the square root of the 10 minus 1. Okay. All right, so now let's do one last problem, then we will take a break and we're going to start video number 2 later. Okay, so this one is a very interesting problem. So since we were in very like maybe elementary school, we already know the circumference of the circle with radius r is 2 pi r. I think maybe in the elementary school, we already know these very popular formulas, right? So now we said, how do I prove it? How do I show it? Okay, this is very interesting. Okay, so very interesting. I really think this is a cool, finally a lot of the formula you took for granted when you were young, and now we be able to show it, prove it. Okay, so let's take a look. I hope I can do it. Okay, this is my circle. Of course, it's not, the center is at the origins here, all right? And now I'm going to find the circumference. I'm going to find the, okay, so I get a better circle. Hope I can get a better one. Just too flat. All right, not bad. All right, so now what I need to do is here. Okay, so I'm going to find a line here. This line I will say this is y equal to the axis here, right? So it's like 45 degrees equally divide this right angle. So, okay, so take a look here. So I know this arc, right? This arc from here to here. So this will be 1/8 of the circumference, right? So if I can find the length of this arc, then I can times what? Times 8. Okay, so now I know this is R. So this is R. So if this is R, okay, so what is this value here? Okay, so what is this value here? Right, because this is a 45 degrees angle. So this value will be what? Is it R over what? The square root of the what? Square root of 2, right? So it's a special triangles here. So this is my X value, right? Okay, so now what is the Y values here, right? So Y value, we know the X squared plus Y squared equal to the R squared. This is my circle formula. So y is equal to the square root of the r squared minus x squared, correct? Y is equal to the r squared minus x squared. I find the function, so I need to use the arc length formula. So I will know the dy dx, or some people say it's f prime x. So what is here? So it's 1/2. Then this is r squared minus x squared negative 1/2. Then what? Then chain rule, right? So chain rule, so it's negative 2x. So if you simplify a little bit, so this will be the r squared minus x squared negative x. Okay, so that is, okay, now we know in here, okay, so I'm going to find the arc length, right? So what is the value of x by the my arc length formula? So the x is from, this is the x, right? So x is from 0 and all the way to what is r over what? The square root of the what? Square root of 2, right? Then the inside will just be 1 plus f prime. So this will be negative x, and this is r squared minus x squared, whole thing squares, right? The dx. So this will be 0 r over square root of the 2. Then this is 1 plus x squared r squared minus x squared dx. Okay, then I combine to find the common denominator. So this is r over square root of the 2. So inside here, when you combine it, it will be r squared minus x squared to the what? To the r squared, right? Because you find the common denominator. So if you find the common denominator, this one will just be the r squared minus x squared, r squared minus x squared, right? And plus x squared, r squared minus x squared. So that's why it's r squared over r squared minus x squared. Then you have a dx, okay? And because I'm on the up boundaries here, so this will be the 0r to the square root of the 2. And what is here? This is r square root of the r squared minus x squared dx. Okay, and now we are familiar with these ones here, r squared over x squared. This is a special what? The trigonometry substitution. Remember that? Okay, so it's a trigonometry substitution. So that's why we can say x equal to the r sine theta. Then I have a dx is equal to the r cosine theta d theta here, right? So now this integration will be, so the r, okay, so I have a r squared minus x squared, r squared minus x squared, so it's 1 minus sine squared. Wow, it's r cosine theta, right? Then times the dx is r cosine theta, so it's r cosine theta d theta. Wow, it's very beautiful, correct? So I have a r cancel, cosine cancel. That's good. So I have this is the r d theta. Okay, so now it's easy. So it's r theta, right? R theta. And what is the theta here? Because x, okay, so this is the sine theta equal to what? X over what? XR, right? So this is the theta. So this is R times x sine what? X over what? X over R. So here, okay. So this is the X over R. Okay, now as you can see, I did not put this the boundaries here because those are the dx boundaries, right? So here is d theta, I did not put that. So finally, when I get this ones here, back to my x, I can put my upper boundary and the lower boundaries here. You see here, all right? So because like I said, you can do the u sub and you put the theta ranges here, but now I think I will prefer just wait when I substitute back to the x, then I can put the original x boundaries here, okay? So now you will substitute these ones here, so you will get a r, okay? So this is the x sine, okay? So you put the r over square root of 2 over r. What is here? So this will give you 1 over square root of the 2. Okay, then minus x sine 0, right? So this will be r. What is the x sine pi? X sine 1 over square root of 1 over square root, that's 45 degrees. So it's a what? It's a pi over what? It's a pi over 4 here. So this is r times pi over 4. What is x sine 0? Is 0 here. So I know this is r pi over 4. So what is the r pi over 4? Remember, it's this pink arc length, and the whole circumference is a times, right? So that's why the circumference is a times this arc length. So it's a times r pi over 4. So it's 2 pi r. Wow, that is really beautiful. See here, right? So we haven't known this formula for a long, long time. And now by the integration use the arc length concept, we can, you know, approach it, prove it in a different way. All right, okay, that's it. So for the first video, we're going to talk about, we will stop here. So basically we talk about this very good formula about the arc length, and we did some example. The last example is really pretty neat examples, right? So we know how to find the circumference of the circle, and now we'll be able to formally prove it. That's really cool. Okay, that's it. So in our next video, we're going to talk about is what is the arc length functions and what's that mean. All right, that's it. And so I guess we'll talk to you and in the next video then. Okay, bye. Have a good day. Okay, bye-bye.